Hello friends, welcome to Abdemi. Let us consider two problems on trigonometric circular functions involving trigonometric circular functions. If x is sine to the power 14 theta plus cos to the power 20 theta, then find the interval in which the value of x will lie. So, how we can proceed? So, we know that for any theta, sine theta lies always in this interval. Sine theta is always greater than equal to -1 and less than equal to +1, and cos theta is also like that. Cos theta is greater than equal to -1 and less than equal to +1. So, sine square theta for any theta is lying in the range 0, 1 closed interval. That means sine square theta is greater than equal to 0, less than equal to +1, and similarly cos square theta also lies in this closed interval 0, 1, meaning the cos square theta is greater than equal to 0 and less than equal to +1. Now, sine square theta is a positive number. Similarly, cos square theta is also a positive number. They can become 0 or 1 for certain values of theta. Otherwise, they are always in the closed interval 0, 1. That means they are both fraction of 1 in general. So, you know, if f is a fraction, that means f is lying in this range 0 to 1, then if you raise the power of n, f by n is a positive integer, then fn is always less than equal to f. I can write, say for example, half is a fraction of 1, so half square is always less than half. Half to the power 4 is always less than half. So fractions have this property. So when the power is raised, the value decreases. Okay, so if f sine square theta, cos square theta, sine square theta and cos square theta, they are functions, they are numbers like f which are lying in the range 0 and 1, and if I raise the power of f by n, then fn, f to the power n is always less than equal to f. And when f is 1, then f to the power n is equality holds. Here I have written this equality sign holds only when f is 1, and similarly here also the equality sign holds when f is 0. When f is 0, then f to the power n can be 0. So with this understanding, since sine square theta and cos square theta behave like this, so I can write sine square theta whole to the power 7 is greater than equal to 0 and less than equal to sine square theta. This is the most important step. Sine square theta being a fraction, sine square theta whole to the power 7 is always less than equal to sine square theta and greater than equal to 0. Similarly, cos square theta whole to the power 20 is always less than equal to cos square theta and greater than equal to 0. So if we add them up, this is cos square theta whole to the power 10. So I can write sine to the power 14 theta is less than sine square theta for any theta, and cos to the power 20 theta is less than equal to cos square theta. Therefore, if you add them up, that means sine to the power 14 theta plus cos to the power 20 theta is less than equal to 1, because sine square, this side sine square theta and this side cos square theta. So I can write like this. So this is, these two we can write using the properties of fraction. Therefore, sine to the power 14 theta plus cos to the power 20 theta is less than equal to sine square theta plus cos square theta. Therefore, this thing is always 1 irrespective of the value of theta. Therefore, I can write sine to the power 14 theta plus cos to the power 20 theta is less than equal to 1. Now what about therefore the upper limit, upper bound of this function sin to the power 14 theta plus cos to the power 20 theta is 1, and it is always less than equal to 1. And what is the lower bound? Now we have seen that individually sin square theta is to sin to the power 14 theta is greater than equal to 0, and cos to the power 20 theta is greater than equal to 0. Individually sin to the power 14 theta and cos to the power 20 theta can be 0 or a positive number less than or equal to 1. But question is whether their sum can ever be 0. Cos to the power 20 theta plus sin to the power 14 theta can ever be 0. Individually they are positive numbers, so when two positive numbers are added, it can never be 0. It can only happen, the sum can only become 0 if individually they are 0. But individually, simultaneously, both cos to the power 20 theta and sin to the power 14 theta cannot be 0. Because you recall the sine and cos curve, sine curve looks like this and cos curve looks like this. So once again let me draw properly. So sine curve looks like this and cos curve looks like this. So whenever sine is 0, cos is either positive 1 or negative 1, and when cos is 0, sine is either plus 1 or minus 1. Okay, so cos theta, when cos theta is 0, sine theta is plus minus 1, and similarly when sine theta is 0, cos theta is either plus 1 or minus 1. So simultaneously both can never be 0. Therefore, the lower bound can never be 0. That means no theta, no real theta makes this sum equal to 0. So it is always greater than 0. This is very important. Therefore, the lower bound of x is not 0. X is always more than 0, but x is always less than equal to 1. Therefore, the range of x is 0, 1, semi-closed interval 0, 1. So, the expression x, which is sin to the power 14 theta plus cos to the power 20 theta, it lies in the range. I think this is clear. So the range, the interval in which the value of x will lie is this thing. This is called semi-closed interval, meaning x is always greater than 0 and x is less than equal to 1. Okay, for no value of theta makes this x 0. So this is the answer. Next problem. See this problem. Apparently the problem looks complicated, but actually it is not so. See how we can handle this problem. So basically it is a series, the summation. There are 13 terms. So if I call this as AS, so AS is basically k equal to 1 to 13 tk. Tk is kth term in the expansion in the series, and the tk, the kth term looks like this: 1 by sine pi by 4 plus k minus 1 pi by 6 plus sine pi by 4 plus k pi by 6. So for simplification, for sake of brevity, I write this angle as alpha k and write this angle as beta k. See, there is an interesting relationship between alpha k and beta k. Alpha k is actually beta k minus pi by 6. Therefore, beta k minus alpha k is pi by 6. This is a very important observation regarding this problem. Now start with the given sum. This is like this. I replace these angles by alpha k beta k. So it looks like k equal to 1 to 13, 1 by sine alpha k sine beta k. Now what I do, this is the kth term in the summation, and there are 13 such terms. Now each term, kth term, I multiply both numerator and denominator by sine beta k minus alpha k. Sine beta k minus alpha k, actually it is beta k minus alpha k is actually sine pi by 6, which is not 0. So I can definitely multiply both numerator and denominator by sine pi by 6. Now in the denominator sine beta k minus alpha k, I replace it by sine pi by 6. So if I replace this by sine pi by 6, that is half. So this 2 comes, and numerator I keep it as it is, sine beta k minus alpha k by sine alpha k sine beta k. Now in each term sine beta k minus alpha k I expand. So what, using the standard formula of sine a minus b. So numerator becomes sine beta k cos alpha k minus cos beta k sine alpha k, and in the denominator it is sine alpha k sine beta k. Therefore the first term contributes to cot alpha k and second term contributes to cot beta k. So with this, what I get cot alpha k for different k values. If I expand, actually it is first term, just plug in k equal to 1. So cot alpha 1 is pi by 4. So cot pi by 4 plus cot pi by 4 plus pi by 6, different values of k run from 1 to 13. So cot pi by 4 plus pi by 6, cot pi by 4 plus 2 pi by 6. Ultimately when k is 13, it is cot pi by 4 plus 12 pi by 6 minus second term contributes what, cot pi by 4 plus pi by 6, because beta k is pi by 4 plus k pi by 6. So if I plug in k equal to 1, first term becomes cot pi by 4 plus pi by 6, second term cot pi by 4 plus 2 pi by 6, and in that fashion if we proceed, then ultimately the final term becomes, last term becomes cot pi by 4 plus 13 pi by 6, and just last but one term is cot pi by 4 plus 12 pi by 6. Now what happens, this after expansion, it is interesting to note that there are similar terms in both the brackets. What are those similar terms? See here, this term and here this term, they cancel each other. This term cancel each other. Here this term, they cancel each other. So I am left with cot pi by 4 minus cot pi by 4 plus 13 pi by 6. But 13 pi by 6 is actually 12 pi plus pi by 6. It is 2 pi plus pi by 6. So I write cot pi by 4 is 1 minus cot pi by 4 plus 2 pi plus pi by 6. But cot 2 pi plus theta is cot theta. So I am left with 2 1 minus cot pi by 4 plus pi by 6. So it is 2 1 minus cot pi by 4 plus pi by 6. I have a standard formula, cot theta plus phi is cot theta cot phi minus 1 by cot theta cot phi. So if I apply this formula, and then we get this expression, cot pi by 4 is 1 and cot pi by 6 is root 3. So if you substitute, then you get this, and finally you get this result. So this is the answer. So apparently the problem looks difficult, but actually it's not so. With simple application of simple trick, close observation of these angles, these two angles, and their interrelation, that is beta k minus alpha k equal to pi by 6, and a simple trick by multiplying both numerator and denominator by sine beta k minus alpha k, then we can could simplify the expression, and ultimately result could be obtained. So these are the problems where simple concepts of trigonometric functions, simple problems, if you apply, then you can solve many difficult problems like this. So I hope if you understand the concepts behind these two problems, this problem and the previous problem, you will get a good insight about the subject, and you will be able to solve similar problems in your exams. Thank you for listening. Thank you once again.